In this video, I will discuss some JEE Main PYQs from the topic Electrostatics. These questions have appeared in the year 2024. Timestamps are given in the description box. You can watch parts of video if you are running short of time. This is the first question. An infinite plane sheet of charge having uniform surface charge density sigma s coulomb per meter square is placed on the xy plane. Another infinitely long line charge having uniform linear charge density lambda e coulomb per meter is placed at z equal to 4 meter plane and parallel to y-axis. If the magnetic values sigma is equal to twice lambda e, then at point 002, the ratio of magnitudes of electric field values due to sheet charge to that of line charge is pi root n is to 1. The value of n is dash. You can pause and run this question. Infinite plane sheet is in xy plane. Let this be x-axis and y-axis let it come out of the plane of the board, and z-axis is towards right. So this is the xy plane where sheet is there. Line charge is placed at z equal to 4. Infinite line charge at z equal to 4. So at z equal to 2, the ratio of the electric field due to sheet, and so this sheet is infinite. So everywhere there will be electric field which is uniform of value sigma by 2 epsilon naught. This can be obtained by Gauss law. This is a result which we'll use here. So at this point, the electric field due to the sheet is this value, and due to your infinite line charge, the electric field value due to infinite line charge is 2k into lambda by r. The electric field due to a point charge is kq by r square. So dimension it is same as q by r, and q by r is dimensionally same as lambda. So it's out the form lambda by r and some constant. In this case, the constant is 2k, where k is 1 by 4 pi epsilon naught. This also can be obtained by using Gauss law. So electric field due to line charge in this particular case at a distance of r is the distance from the source, which is 2 here. So 2k into lambda by 2, and electric field due to the sheet is sigma by 2 epsilon naught. So the ratio ES by EL, sheet by the line charge, will be, it's k lambda sigma by 2 epsilon naught by k into lambda. K is 1 by 4 pi epsilon naught. Epsilon naught will cancel. So 4 pi, if it goes up, it will become 2 pi, 4 pi by 2 into sigma by lambda. Sigma by lambda is 2. So this 4 pi, this has to be compared with 4 pi by 1. This has to be compared with pi root n by 1. So this means n should be 16. 16 is the correct answer. This is what I explained here. The sheet, infinite sheet, is in the xy plane, and z-axis there is a infinite line charge at z equal to 4. So this is a right-handed coordinate system where x cross y is the direction of z. So electric field in infinite sheet is sigma by 2 epsilon naught, and due to line charge is 1 by 2 pi epsilon naught into lambda by r. Here r is 2, the distance from the source. So the ratio is this by this, which is 4 pi. This has to be compared with pi root n. So n is 16. This is the next question. The distance between charges q and minus q is 2L, and between plus 2q and minus 2q is 4L. The electrostatic potential at point P at a distance r from center O is minus alpha into QL by r square into 10⁹ volts, where the value of alpha is dash. Use 1 by 4 pi epsilon naught is 9 into 10⁹ in SI units. So here, this can be considered as two dipoles. One dipole is Q plus Q, another dipole is minus 2Q and plus 2Q. We'll make the assumption that R is much greater than the size of the dipole. It's not given in the question, but we have to make that assumption to use the dipole formula. For a dipole, the potential at a point where dipole approximation is valid, where that is R much larger than the size of the dipole. It's K P dot R cap by R. For a point charge, the potential is of the form K into Q by R. So dimension of this is same as K into Q into R by R square, and Q has got the same dimension as P. So potential to the first dipole minus Q plus Q, K into P is the charge with the separation which is 2L, and P1, the first dipole, it's in this direction, and R cap is from the origin to the source. This is the R cap direction. So P dot R cap is cos 60. The angle is 60 degrees. So P R cap is 1. So magnitude of P is Q to this one divided by R. Second dipole, potential due to it is K into P2 is charge is 2Q, and the separation is 4L from here to here. Divided by R into cos of the angle between P2 is from this to this. The direction of P is from minus charge to the plus charge. So this is P2 direction, and this is the R cap direction. So the angle between those two is 120 degrees. So cos 120 degrees. Cos 60 is half. Cos 120 is also half, but it's in the second quadrant, so it's minus half. So the total potential is, by superposition, sum of the individual potentials V1 plus V2. So K, if we take QL by this R square, because for a point charge it's QK by R, and will become by R square for a dipole. So QL by R square. So this half and this 2 will cancel. QL by R square, so it's just 1. And then here will become minus. This is 4 2s are 8. So 4. 2 into 4 is 8. 8 by 2 is 4. So 3 times K minus 3 times K into QL by R square. QL by R square is there, and then 3K should be compared with this one, and K is 9 into 10 raised to 9, so this is equal to minus 27 into 10 raised to 9 into this QL by R square. So comparing this thing with this one, we get alpha equal to 27. Is the correct answer. So this would explain here. For a dipole, the potential is K, which is 1 by 4 pi epsilon naught into P dot R cap by R square. This is due to a dipole P at a distance R from the center of the dipole. So the first dipole, the charge is Q and separation is 2L, and the angle between the polarization vector and the dipole moment vector and the R vector is 60 degrees. The angle is 60. And the second dipole, the charge is 2Q, separation is 4L, and the angle is 120 degrees. So it's minus this one. So the total potential is sum of these two by superposition principle. Comparing this with the given expression, you get alpha is 27. Next question. Two identical charge spheres are suspended by strings of equal lengths. The string make an angle 30 degrees with each other. When suspended in liquid of density 0.8 gram per centimeter cube, the angle remains the same. If density of the material of sphere is 1.6 gram per cc per centimeter cube, the radial constant of the liquid is. So there are two charges attached to your strings, and there is a fixed support here. So the force acting on this charge is its weight mg downwards. Tension of the string. Two identical charges, so there will be a repulsive force. In the second case, the same thing is immersed in a liquid, but the angle remains the same. This angle is 30 degrees in the first case. In second case, also same 30 degrees. But in the second case, since it's immersed in a liquid, in addition to the weight, there will be a buoyancy force due to the immersed liquid, and this repulsive force will change to a different value because the electric field or the Coulomb's law, the force between two charges 1 by 4 pi epsilon naught, and if there is a direct medium, it's K epsilon naught. And tension in the string, which could be different from the first case, T2. But the angle remains the same. So for it to remain same, what is the dielectric constant? So let this angle with the vertical be theta. Here also the same angle because this has not changed, same theta. So here you get T cos theta equal to mg, vertical force balance, horizontal F equal to, or I can write T sin theta equal to the electrical force F. In the second case, the F will become reduced by a factor 1 by K, where K is a direct constant. So T2 in the vertical direction, the buoyancy force will reduce the effective weight. And in the horizontal direction, T2 sin theta equal to F by K, where F is the force of repulsion in the first case. So from this, I'll get, if I divide these two, I'll get tan theta as F by mg in the first case. Second case, tan theta, it's F by K by mg minus the buoyancy force from this K equal to 1 by 1 minus the buoyancy force by mg. Buoyancy force is the weight of the liquid displaced. That is same as the volume of the sphere into density of the liquid into volume of the sphere into g, and mass of the sphere is density of the sphere into volume, which is same, into g. So this quantity is this one. So the ratio is ratio of the densities. So K is 1 by 1 minus density of the liquid 0.8 and the density of the sphere is double 1.6. So it's half. So this is equal to 2. So option D is the correct answer. So this is what I explained here. In the first case, the two charges, it's making an angle 30 degrees. In the second case, the whole thing is immersed in a liquid because there will be an upward buoyancy force. So the tension will become different, T2, and this electrical force of repulsion will go down by a factor 1 by K because Coulomb's law, the force between two charges is 1 by 4 by epsilon naught, Q1 Q2 by R square. But if it's a direct medium between the two charges, then the force is 1 by 4 by K epsilon naught. So here in this case, T cos theta is mg in the vertical direction, and the horizontal force component is T sin theta equal to F. Same thing if I write here, it will be T2 cos theta equal to effective weight, which is mg minus the buoyancy force, and in the horizontal direction is T2 sin theta equal to F by K. So dividing these two, I'll get F by mg as tan theta. From here, I'll get F by K by mg minus b. So from this, I'll get K as this one, and the buoyancy force is the weight of the liquid displaced. So the density of the liquid in the volume of the sphere, and this m is density of the sphere into volume of the sphere. So this ratio will become ratio of the densities of liquid and solid. Next question, two charges minus 4 microcoulomb and plus 4 microcoulomb are placed at point A 104 meter and B 2 minus 15 meter. Located in electric field E equal to 0.2 I cap volt per meter. The magnitude of torque acting on the dipole is this much, where alpha is. Torque on a dipole, the formula is P cross E, that can be derived. Torque on a dipole when placed in external electric field E is P cross E, and P is the charge. Here it is 4 micro coulomb. Into the separation, which is, and it's a vector, so it's AB vector. It's from negative charge to positive charge. Negative charge is at A, so it's AB vector cross electric field vector is also given. So AB vector is B vector minus A vector. So it's B minus A. So 2 minus 1, it's 1, minus 1, minus 0, minus 1, 5 minus 4 is 1. So this is vector I, 1 I cap minus J cap plus 1 K cap. You can also written as a triple. So dot cross product of two vectors. So this number I can combine 4 into 0.2 is 0.8 micro. So that's 8 into 10 raised to minus 5. And the cross product of two vectors I can get in terms of determine I cap, J cap, K cap. First vector 1 minus 1, 1. Second vector 0.2 I've already taken care here. So just 1, 0, 0. So I can expand this determinant along this one, this row. So just 1 into so 1 into j cap sk cap. Okay. So magnitude of this vector is magnitude of this quantity, which is 8 into 10 raised to minus 5, and magnitude of this vector is root 2. So this we have to compare with this one. So alpha is 2. Two is the correct answer. So torque on a dipole is P cross E. This is the formula. This can be derived easily because torque is R cross F. From this we can derive this one. So P vector is the charge into the separation between the two charges, and P direction is from minus Q to plus Q. So here the minus is minus Q plus Q, the direction is A to B. Electric field is given. So Q is 4 microcoulomb, and then A, B is B vector minus A vector. So B minus A is this one. And cross product two vectors can be written in terms of determinant. First vector is 1 minus 1, 1. Second vector is, this is just 1 because 0.2 is multiplied here. It's 1, 0, 0. So this I'm expanding along this row. So 1 into this determinant, which is this one. Magnitude is root 2 of this one. So alpha is 2. Next question. An electric field is given by 6I cap plus 5J cap plus 3K cap Newton per coulomb. The electric flux through a surface area 30I cap meter square lying in YZ plane in SI unit is. So flux through a small surface, say dA, is E dot dA, and this small flux is d phi. So this is E into dA into cos of the angle between the two vectors E and dA. So get the total flux coming out of finite area, you have to integrate this one. But over the surface, if E is not changing, if E is uniform, and theta is also uniform, so E cos theta will come and then integral dA, which is the total area A. So this can also be written as E dot the area vector. So this is valid when the electric field is uniform and theta is also uniform. The angle between the electric field and the area vector for all the area elements is same. In this case, electric field is uniform and the area elements, or each of the area element is also direction is same. So here in this case, electric field is just the dot product of these two. So I cap dot with I cap will give me 6 into 30 is 180, and then I cap dot j cap is 0, I cap dot k cap is 0 because dot product of two perpendicular vectors is 0. So this is in SI units, because this is SI units, that's also SI units. Three is the correct option. So this one explaining here, the flux coming out of small elemental area ds is E dot ds, which is E into ds into cos theta with theta's angle between the electric field vector and the area element. To get the total flux coming out of the finite area, we have to integrate this thing over all the elements. And suppose it turns out that the electric field is uniform, it's not going to change from element to element, and theta, the angle between the electric field and the area element, is also not changing from element to element, then this E cos theta can come out of the integral, become integral ds, which is the total area S. So this can be written as E dot S. So here in this case, E dot S is 6 into 30.